All right, everybody, really fun video here. We're gonna walk through a muscle contraction. So a lot of stuff to cover. We're gonna start with some pictures though. So we're gonna draw out where we're gonna communicate between the neuron and the muscle, label some parts, and then we'll talk about what those parts are doing, because that's really how you kind of build a story. Start with the anatomy, know what's there, and then how they interact. So we're gonna start where that axon comes down towards that muscle. So we have an axon of a motor neuron, and we send an action potential down that. So we're sending a signal down this axon. So remember, the job of an axon is to send electrical information. And the reason why we send that electrical information down is because inside of that synaptic knob, we have these vesicles containing neurotransmitters, the chemical messages. So here's our synaptic knob that's containing the vesicles. And since we're talking to a muscle, specifically the neurotransmitters in there is acetylcholine. So ACH is the abbreviation. So we're going to send that message to a muscle. So on the other side of a space, there's always a gap between these cells, they don't directly fuse to them, is going to be an area of the muscle where we're going to have a lot of folds. Ooh, that has a nice squeak sound. So here's our muscle cells. So it's going to be really big. So remember, when we're talking about skeletal muscle, these are giant cells that have actually formed from multiple cells merging together. So this right here, everything down, kind of picture this as being inside of the muscle fiber. That space inside of there is called the sarcoplasm. The membrane is going to be the sarcolemma. Specifically, the part of the membrane where you have folds is going to be the motor end plate. So all of this over here, from here to here, is your motor end plate. So let's talk about why we have the folds. We're releasing a neurotransmitter called acetylcholine. You have that message binding to receptors on the other side. If you put folds, now you have more room for these receptors. So you can kind of picture them all along the whole thing. So when we release acetylcholine to that space, by the way, we should probably name that space. So that's the synaptic cleft. You can also call it a synaptic gap. Either one's fine. So when you release acetylcholine into the space, we have more receptors for it to bind to by having the folds on that motor end plate. Now, just to kind of keep track of what exactly we're looking at here, we have a neuron communicating to another cell. So we have a synapse. Now, specifically the synapse, when we're talking about a neuron talking to a muscle, we're going to have three structures at play here. We have the synaptic knob, the space that they release their message into, and then the space where you have your receptors to understand the message. So these three things make up what we call the neuromuscular junction. So the communication between a neuron and a muscle. And it's a junction because it's where they're meeting. All right, so that's a lot of the anatomy. Now we're going to walk through the steps. So let's start with the signal that comes down that axon. So we're going to start with number 1 over here. So our number 1, I'll put it right here, is an action potential, goes down the axon of a motor neuron. Then we're going to get those vesicles to release acetylcholine. So what will happen here is our little vesicle is going to go to the edge and fuse with the cell membrane. And when it fuses, it opens up. And now acetylcholine is free to enter that synaptic gap or synaptic cleft. So this will be our second step. So number 2 is we're going to get vesicles to release acetylcholine. Remember, ACH is the abbreviation for acetylcholine, into the synaptic, and you use cleft or gap. Now here's an important part. What happens when you get into the gap? Well, you're going to go across in an area of high concentration to an area of low concentration. So we're going to, the word is diffuse. So 3, acetylcholine diffuses across synaptic cleft. Then it binds to that receptor there. That receptor is a gated ion channel. So what will happen is out here in this space isn't just acetylcholine, but a lot of sodium. And so what will happen, you bind to the receptor. That receptor is a chemically gated ion channel. So we're going to open up the doors and we're going to let sodium in. So once we bind to the receptor, we're going to let in positive ions. So 4-ACH binds acetylcholine receptors. So I'm going to say ACH receptors. On what space? What was this called again? Motor end plate. So on the motor end plate. Now this is the moment where now the muscle knows that there's something going on. The muscle has now been signaled. So this is where you initiate stuff from the muscle. So I'm going to switch colors. So this right here is kind of all electrical and then kind of more communication. And now we're going to shift into, now it's the cell itself, the motor, or the motor components kind of taking over. So we're going to have the signal being created in the muscle now. So ACH binds to ACH receptors on the motor end plate. That opens, so 5 here, opens sodium ion channels. That means sodium's going to go in because it will always follow your concentration gradient. So specifically, it's entering the sarcoplasm. And remember, when you have a flow of charges, specifically a flow of positive charges, that means you're creating an action potential. So when we have the sodium ion channels open up, sodium coming into the sarcoplasm, we're creating a signal, an electrical signal. So this creates an action potential. That action potential, and I'm just going to kind of draw it as a squiggly line like I did before, is going to go across the cell membrane. And now we got to get it deep into the cell. We can't just keep the signal up here at the edges. We have to have ways for the signal to get into this muscle fiber deeper, because remember, these are really wide. And so we're going to have a part of the muscle fiber that dips down into our cell and comes back up. Woo! And that right there is called the transverse tubule, or T-tubule. And so we're going to have that electrical signal go across the sarcolemma and then down that transverse tubule. So now the action potential spreads across sarcolemma and transverse tubule. We can call it T-tubule. So that's what our 6 is. Got the signal spreading. So we started with an electrical signal. It turned into a chemical signal. We're creating another electrical signal. The difference is just which cell you're on. So up here, you had an electrical signal in your motor neuron. Chemical signals released to communicate between the two cells. We create another electrical signal. Now this time we're in the muscle fiber. We're going to send that signal deep so we can have more of the cell understand, like, oh, it's time to do something. But again, we're going to have the same pattern. We're going to go from an electrical to a chemical message. Now inside of our muscle fiber, we store the chemical message in something that kind of looks fancier than what I'm about ready to do. So for now, we'll just picture it as like a little storage box. That's the sarcoplasmic reticulum, which a lot of times you'll see abbreviated as SR. Inside of that SR is a bunch of calcium ions. And those calcium ions are the chemical message that we want to release. And so our next step, we have the electrical signal coming down, because that electrical signal will open up voltage-gated ion channels. They open in response to a change in charge to let calcium out. So 7, open calcium ion channels in the SR to release those calcium ions. So now they're out into the cytoplasm. This is where the art gets really, really rough. So I'm actually going to switch us over to textbook art because it's way better than what I'm capable of. So some pictures first that kind of go with what we've already done. We have in this picture your neuromuscular junction. In the blue, you see the synaptic knob. You then have the vesicles stored there, the acetylcholine, and then you have the gap, the synaptic cleft or gap. So we're going to have an electrical signal spreading across that synaptic knob, telling us to release acetylcholine. So now that acetylcholine is going to be let into the synaptic cleft. It's going to diffuse across and bind to receptors on the motor end plate. That's going to create another electrical signal because those receptors are chemically gated ion channels. So when the molecule binds, the ACH binds, you're going to open up the door and you're going to let sodium in. That's creating an electrical signal. That electrical signal is going to spread across the sarcolemma, down the transverse tubule, and then you're going to get calcium to come out of the sarcoplasmic reticulum. And that's where I've kind of left you in my picture because it's hard to draw it after that, because here's where we're going to go. Those calcium ions are going to go bind to troponins. Remember, troponin are like the little handles on those long ropes that hide the binding site. So step number 8 is calcium binds troponin. So we can kind of see it in the picture. We have the calcium little green circle going to the little blue brown thing, not blue. And actually when that binds, you get a chemical reaction, you get a change in shape. So it's going to move the little rope. Do you see the rope that's kind of weaved in with it? So we're moving that rope. That rope's called tropomyosin. So the calcium binding to troponin causes a shape change, which then moves tropomyosin away from the myosin binding sites. I guess let's real quick kind of make sure we're all on the same page of what we're dealing with in this picture. So we have those circles, those are actin. On actin, there's that yellow part, that's where you want to bind if you're going to get a contraction to happen. Those are covered with something called tropomyosin. So actin is a circle. Tropomyosin is the rope that hides them from the thick filament. I told you I wasn't going to draw it because my art wasn't as good. I'm still drawing it. So we have tropomyosin. That's the rope that's in the way. And then we have the little handles that'll change shape. That's the troponin. So that's what we had going on there. The calcium's attached to the troponin. It changed its shape to move the tropomyosin away from those binding sites on your thin filament, on your actin. So that's where those are. So tropomyosin is moved away from myosin binding sites on actin. Our next step, because now those myosin binding sites are available, the myosin heads will attach. We call that a cross bridge. So we're going to form a cross bridge. So myosin head binds with actin. That's called a cross bridge. So now we're attached. Thick filament's the myosin. That's the bigger thing that you see at the bottom of your screen and again at the top. You're attached. The next move, you gotta pull it. So now we're gonna do a power stroke. We're gonna pivot towards the M line or the middle of the sarcomere. So that's your 10. So myosin head pivots. So you're pivoting towards the M line. You're pulling it towards the middle of the sarcomere. That's your power stroke. You'll then release it using ATP and then repeat the whole process all over again. So then we're going to be set back to your original position. So 11, myosin heads release. So you're going to let go of the actin. And then you're just going to repeat that step 9 and 10, and you're just going to kind of keep doing this all over again. So you're just going to kind of keep recycling over and over again. The goal basically is you're going to keep pulling towards the M line. You're going to take turns. Not all of them are going to grab on at the same time, pull, and then let go at the same time. It's like this one reaches up to the thin filament, pulls towards the M line. This one will let go, but before it lets go, you're going to have this one come over, grab it, and then this one lets go, this one pulls. So you're just kind of taking turns back and forth. You don't really get to see that in this picture. But here we got another relaxed position. We're going to grab a hold, we're going to pull. We're going to keep repeating. Take ATP to remove it, reset, grab a hold, pull. So you're going to keep doing that over and over again to make that contraction happen because you're shortening the sarcomere. And that's the job of a muscle contraction. Hopefully that all makes sense now that you've seen it all drawn out and with some different art. Thank you. So you're just going to kind of keep recycling over and over again. The goal basically is you're going to keep pulling towards the M line. You're going to take turns. Not all of them are going to grab on at the same time, pull, and then let go at the same time. It's like this one reaches up to the thin filament, pulls towards the M line. This one will let go, but before it lets go, you're going to have this one come over, grab it, and then this one lets go, this one pulls. So you're just kind of taking turns back and forth. You don't really get to see that in this picture. But here we got another relaxed position. We're going to grab a hold, we're going to pull. We're going to keep repeating. Take ATP to remove it, reset, grab a hold, pull. So you're going to keep doing that over and over again to make that contraction happen because you're shortening the sarcomere. And that's the job of a muscle contraction. Hopefully that all makes sense now that you've seen it all drawn out and with some different art. Thank you.